Okay, let's start second talk. Aninda will continue the lecture. Thanks.
Okay, so this is my final lecture, and so in this lecture, I'm going to give you a flavor of the kind of questions that one can tackle using the formalism that we have developed so far. And in some sense, this is complementary to a lot of recent activity in this program. This is a partial list of references. Justin is there in the audience, so in case you want to find out about the complementary approaches, please feel free to talk to him. So the plan of this lecture is that in the first half, I'm going to give you this flavor of what investigations you can carry out. And so getting into the numerical bootstrap program can seem a bit daunting to the uninitiated, especially to figure out the nuances. So in case you want some more details, I would encourage that you come and talk to Justin and Devapriya, who's there in the audience, who can actually help you get started. So the first half, I'm going to give you a flavor of what you can do with the kind of questions that you can ask. And this is a very small sample of the kind of questions that you can ask. It's just limited by the creativity that you have. And in the second half, as I mentioned yesterday, the second half is going to be sort of using the dispersion relations, and this is using dispersion relations that are standard fixed T and derive what is called the Frossa bound or the Frossa-Martha bound, and that this is going to be a black on the green board. So far, what we have learned in the last 3 lectures is that there is a new sort of a stringy dispersion relation, and I've given the unsubtracted version, which is symmetric under S1 and S2 interchange. So this is the dispersion relation that you would use to understand the scattering of colored scalars, where you typically have 2-channel duality or 2-channel symmetry. Or this could be also used to understand the form factor in gluon scattering. And as I mentioned, the key takeaway here is that unlike the fixed T dispersion relation, there's a parameter lambda that is sitting in the dispersion relation here, which in some sense is the elasticity parameter that the string worldsheet picture gives us. So there is no string worldsheet in this dispersion relation. So although it was motivated by thinking about string theory, we wanted to somehow extract some good features of string theory and write down something that would enable us to maybe go away from string theory, because as we know that we have not been able to make any connection with phenomenology so far. And this picture is trying to be smart aleck. And because of this lambda, you can actually extrapolate between various known dispersion relations. And those of you who have seen the M-theory web of dualities will see that this has been deliberately designed in that way to make you, or to subconsciously give you the impression that this must be the right way of thinking about things. So basically, there are 5 known dispersion relations now in the literature. So fixed T, fixed S, and fixed U are things that are the familiar ones that people have been studying for a very long time. CSDR stands for crossing symmetric dispersion relation. So again, the original idea of this crossing symmetric dispersion relation is not new. It was from the 1970s. But it was resurrected for different reasons over the last 5 or 6 years or so. And then there is also something called the local crossing symmetric dispersion relation, which is sort of an offshoot of this crossing symmetric dispersion relations. I won't go into all this, but basically these are the 5 dispersion relations that are known to us. And as I said, this parameter that we have introduced, lambda, interpolates between all this in various limits, and the limits are actually indicated in that figure. So, and I should also say that this is based on work, a couple of papers that we wrote over the last year or so. Bhatt is Faizan Bhatt, who's my graduate student who's graduating this year. He's going to Italy for a postdoc. He was sitting in the audience. Arnab is a postdoc in ISC. And the second follow-up was released last week. So the idea is, again, we want to generalize string models. We don't want to, so first of all, we want to write down a set of equations where string theory is a solution. So because we know that string theory is somehow a consistent quantum field theory, so at least whatever equations we are trying to solve should give string theory as an output. And then we will try to see whether we can generalize the solutions of these equations. So the philosophy is that we want to examine a class of superstring-like models. And in this particular case, it's superstring. We will focus on the open superstring theory, which is relevant for gluon scattering. So what you do is you take the dispersion relation and you do a partial wave expansion. One of the assumptions that we are going to do right now is that we're going to put in an integer space spectrum, which is similar to the kind of spectrum that you see in superstring theory. And that is why, so what you do is you start off with this, this formula and then do a partial wave expansion. So I hope that people are familiar with the partial wave expansion. So you start off with your amplitude, m of st, and then up to some normalization factor, you write this in terms of partial waves. So there is these partial wave amplitudes, and then they are typically weighted by a version of the Legendre polynomials. So depending on whether you're scattering massive or massless particles, it will be either one, the argument of the Legendre polynomial is going to be either 1 plus 2t over s, or if you're scattering massive particles, say pions, then you might also see s minus 4m squared. But for now, we are scattering gluons, so this is going to be the partial wave expansion. And the imaginary part, or the absorptive part, is also going to look similar. It looks like so. And let's call this eta L. So this is the imaginary part. Eta L is the imaginary part of FL. And then you again see the partial wave, the Legendre polynomials. So the G's that you see in this formula here are the generalization of the Legendre polynomials in higher dimensions. These are called the Gegenbauer polynomials. And so if you put D, this is the space-time dimension. So if you put D equal to 4, you get the Legendre polynomials back. And the Gegenbauer polynomials and Legendre polynomials have some common properties. So there is some orthogonality property that the Legendre polynomials satisfy. And that's the reason why you have this 2L plus 1 factor outside. And one of the conditions that you get from unitarity is that this eta L is bigger than 0 or bigger than or equal to 0. And this is this follows from unitarity. So what we do is, this is the thing that is needed. So we put that into this dispersion formula. And so instead of T, you have this combination that, that is there in the second argument. And that's the reason why the expansion looks a little bit more complicated. You don't literally see 1 plus 2t by S. You actually see 1. This is the version of T that enters the dispersion formula. And as I said, that we have specified integer spectrum. And that is why instead of S, you see an integer there, n. N is an integer here. And for convenience and for technical reasons, I have subtracted out the massless part. So this is the, so what are the unknowns here? So I have specified the tree-level spectrum. The unknowns are basically these partial wave amplitudes. So these are not fixed. So if you put in the string amplitude, you would know what these CLNs are. You can compute them. And the constraint that this amplitude satisfies is first, unitarity. So this has to be bigger than 0. And second, there is this parameter that is sitting here, lambda. This amplitude has to be independent of lambda. So these are the two constraints that we are going to impose while trying to constrain these CNLs. Is that clear? Okay, so some data that you need to know so that you have a point of comparison. So if you take the low energy expansion of superstring, so you're scattering gluons, so the f to the 4 actually tells you about the helicity structure that the gluons have, and then it is multiplied by this amplitude m of st, which is symmetric under st interchange. Now this should look familiar to you. This is almost the Euler beta function, except that there is this one shift in the denominator, and that is peculiarity of superstring theory, that instead of literally seeing the Euler beta, you have this one shift in the denominator. If you carry out a low energy expansion, by low energy expansion, I mean literally take this and series expand this around s and t, both small. And let's series expand by pretending that they go to 0 at the same rate. So you'll get a series expansion of this form. So you will see these Euler zeta functions appearing. So I will repackage this series expansion in some way and call the coefficients of the term the constant term W00, which is zeta of 2. And then you see the linear term, that is zeta of 3 here minus zeta of 3. And then when you go to next order, you'll get a quadratic term. And the quadratic term, you have to be a little careful because there are two kinds of quadratic invariance. Either it's s times t or s plus t square. So you have to extract the coefficients carefully. Oh, sorry. This is you're right. This is W01. This is a typo. Thank you. And so the numbers that you need to remember is that this constant W00 is roughly 1.6. And W10 is minus 1.2, and W01 is 1.89. So this is the data that you should keep in mind, and if you don't remember, don't worry. But the sign of W10 is kind of important in my conventions. It's negative, and W01 is positive for string theory. So basically, these three are going to be the main players in constraining the space of S matrices. So W10, W01, and W00. Yes. Yeah, sorry. I was making this idea right. It's minus 1.644. Correct. Thank you. So next question is, how do you constrain? Because now I said that the C and Ls in the basis are going to be positive. And then I said that the amplitude has to be independent of lambda. But then typically in this numerical bootstrap game, we try to extremize something or the other. So you could either say that we are going to find the maximum value allowed by these constraints for the Wilson coefficients. And so typically people look at the space of theories in the W10 and W01 space. And one of the things that people search for are interesting features, especially kinks in these space of theories, because the logic behind looking for kinks is that you're trying to rule out space of theories, and suppose there is some isolated point where there is an interesting theory. All the neighboring points are trying to get ruled out, and as a result of which you're going to see a kink in that space of theories. So I like to joke that numerical bootstrap people are kinky people. So, but the reason behind looking for kinks is precisely this. So we are going to do it a little differently. What we're going to do is we're going to span the space of W10 and W01, except we are actually now going to minimize minus W00. So the constant W00 that was there in the low energy expansion, we're going to minimize minus of that quantity. And the reason, the physics reason behind doing this is you can actually relate that quantity to the first finite moment of entangling power. So you're scattering particles, you're generating entanglement, and this entanglement is going to be generated in the helicity space. And why we want to minimize entanglement or the amount of entanglement generated is because I have an experimentalist wife and she works in quantum computing. And I know from her that making entangling gates in a lab is very hard. So, in a kind of a quantum circuit, you would expect the number of entangling gates to be as low as possible. So that is the sort of the philosophy why we want to minimize this entangling power. And what happens, and I'm going to show you some plots in a bit, that if you fix your W10 and W01 to be the superstring values that I showed in the previous slide, you basically recover the CNLs, which are extremely close to the superstring expected answer by doing this, by playing this game. Okay, you might have thought that if I fix the low energy coefficients, then maybe that has something to do with fixing all the rest of the CNLs, but that is not to be expected because you are expanding around s equal to 0, t equal to 0, and there's no reason why this expansion should know about all the remaining poles that are there in the theory. So how do we do this? So there are two methods. So one method is that you can use this package that the conformal bootstrap people, in particular David Simmons-Duffin, has developed over the last several years, which is called SDPB. So SDPB stands for Semi-Definite Programming for Bootstrap. And when you do that, as I said, that we require to specify that the amplitude is independent of lambda. So you have to impose this kind of a condition. And of course, because we are working with truncation, you cannot literally impose this equal to 0. So best you can do is specify some tolerance, and that tolerance can be some ad hoc tolerance. And by specifying this ad hoc tolerance, you can implement all these constraints in using semi-definite programming for Bootstrap. You can try to do this directly in Mathematica, except Mathematica does not allow you to go to very high precision, whereas SDPB does. The second method, and this is also, there are two ways of thinking about this, and I'll tell you why we decided to use this, is to use machine learning. And one of the reasons is that numerically we have to work with level truncation, and we have to impose these conditions. And so instead of specifying some ad hoc tolerance, we basically want to impose constraints of this kind, that if you have two different values of lambda, then they have to be equal to each other up to some thing that we can identify as the error. Okay, so we want to impose this kind of a constraint, and this turns out to be a nonlinear constraint on these partial wave coefficients. And that is why this cannot be imposed directly in SDPB. So trying to use some nonlinear optimizer or trying to use machine learning is a good idea here. And of course, the other reason and the other physics reason is that we want to learn these CNLs as a function of L and N. And because these right now have an existence when L is an integer and N is an integer, but we want to learn it as a function of L and N. And the reason is because we want to investigate questions like where is the Regge pole? There is a theorem in complex analysis called Carlson's theorem, which tells you that if you know the value of a function at integer points, and if the function has a fast enough fall off, then you basically know the function everywhere. So machine learning is a potential way of implementing learning the function everywhere. And the more practical reason is that you want to have fun, you want to do something fundamental, you want to think that you're, of course, many people get into theoretical physics because they want to explore something really fundamental, hopefully contribute to the discoveries. But at the same time, you want to keep building on your employability, and working on a project that uses some of these modern techniques like machine learning is a good thing to keep in mind in case you are forced to go into data science or something else. Okay, so how does the new dispersion relation help? So another way that the new dispersion relation helps is that you can impose constraints. So this is a grid. So this is S, the x-axis is S. I've relabeled it as S1, and S2 is T. So you want to impose constraints, these kind of constraints on a grid of points, and you want to do it on as big a grid as possible. And this new dispersion relations enables you to actually impose this on a very big grid. If you had the fixed T dispersion relation, then you would be forced to only keep T to be negative, and as a result of which you wouldn't be able to access a lot of interesting points. So this is the output of this game that we play. So we are minimizing this minus W00. So this is the exact answer that is expected from string theory. So the first column is from the known answer, and the second column is from this numerical game that we play. So this is what you get for what is called the leading Regge trajectory. This is the first daughter, and this is the second daughter. As you can see, let's pick a random point, say n equal to 6, and you can compare the two rows, two columns, and you can see that they are reasonably in good agreement. And you pick some other random points, say n equal to 18 for the second daughter, compare these seem to be in reasonably good agreement, and so on. So there are some mismatches. It's not a completely exact agreement, but the agreement seems to be very, very good. For some reason that we have not completely understood for higher ends, the agreement seems to improve so far as the subleading daughters are concerned. So in this particular case, the way that we did it was using SDPB with some ad hoc 10 to the power minus 9 tolerance. So when we impose this condition, we just said that this should be 0 up to 10 to the power minus 9 accuracy. So you can play this game by varying the Wilson coefficients, so W10 and W01. So if you remember the values, W10 was negative, minus 1.2. So that red triangle there is the string amplitude. The values corresponding to string theory. So this is a heat plot. And what does this various colors mean? So the blue region corresponds to amplitude where the S channel and T channel are approximately equal. So if you see a blue color, then this worldsheet duality or the dual resonance hypothesis is more or less pretty well satisfied. And the other shaded regions, the duality hypothesis is not very well satisfied. And so there has been some analysis of deforming the open string amplitudes, open superstring amplitudes, finding deformations. In particular, there are these hypergeometric deformations, and these hypergeometric deformations were, for the open superstring case, were written down by Marcus Pradlin and his undergraduate student, Mansfield, in 2024. This black line, solid line here, actually corresponds to the hypergeometric deformations. And as you can see, it just passes through the center of the blue region. So this numerical way actually explores the space and finds all kinds of interesting deformations of the open superstring amplitude. Okay. Now, the dispersion relation enables you to actually frame the problem in a different way. So you can actually frame it by demanding that you are allowed to have higher subtractions. So the first non-trivial higher subtraction basis is what we will refer to as the non-dual amplitudes. And why are we looking for this? So if you remember, one of the reasons was in the first lecture, just to remind you, I had pointed out that there was evidence, which was through this Chu-Frotchi plot, that you have resonances, spin versus m square that is almost a straight line. And there was some evidence that this was in agreement with Regge theory. Why some evidence? Because experiments, Regge theory corresponds to having an asymptotic expansion of the amplitude. And when you compare with the experiments, you really can't go to asymptotic energies. So that is why I use the word some evidence. But one thing that the string amplitudes definitely had, which realistic amplitudes are not expected to have, is exponentially soft behavior in the fixed angle limit. So we are trying to examine if this numerical bootstrap can give rise to interesting amplitudes which have other kind of reggae behavior as well as behavior that is not as exponentially soft. So this enables us to examine that question. So let's assume that the amplitude needs higher subtractions, and you can rerun the game again with the higher subtraction. So we have just put in one subtraction here. Again, you get a space of theories. And now there is no reason to expect the dual resonance hypothesis to be satisfied. In spite of that, this red triangle, which corresponds to the Wilson coefficients for the string value, again is picked out to be a model that satisfies its dual resonance hypothesis. But on the other hand, there are these interesting S matrices, the black star here, which does not obey this duality hypothesis. And in particular, this black star here, instead of actually giving an amplitude that keeps on decaying, so this is the absolute value of the amplitude. So to plot this absolute value, I've given S an imaginary part so that we don't see these infinite delta function spikes. So this is the absolute value of the amplitude for some fixed value of small t plotted against S. So this is S. And so this black line here is the string amplitude, which actually decays, and this is expected because we have fixed t to be negative, and it's supposed to die. It has the reggae behavior, but there is this other guy here, this amplitude. It actually goes to a constant at high energies. So it definitely has a different kind of reggae behavior than what string theory does. So in fact, when you actually compute from the amplitudes the reggae trajectories, so reggae trajectories are just you're looking at the amplitude and you're doing a high energy fit, and you're basically you're trying to find a fit of this kind. So alpha t as a function of t by looking at the high energy fixed t limit. So the red line, the blue line and red line are on top of each other in the positive t region. So the red line is what you get from the numerical open superstring amplitude. It should literally be a straight line, except that because of numerical truncation, you see a small curvature. So this curvature should not be taken too seriously. But this blue line, which was for the black star model, actually has a very interesting behavior. It turns over and becomes a constant. So this is something completely unlike what you expect in string theory. And fixed angle is very nice. Fixed angle means your z, which is 1 plus 2t by s, you are holding that fixed. And you have this exponentially soft behavior for string theory. So this red line corresponds to the string amplitude. It really dies very, very fast. So these are for different values of z. So z 0.99 is almost in the forward limit. So what happens is that the blue line is for the black star model. So in the black star model, as you can see, it is not as exponentially soft as string theory. And in fact, it seems to approach a constant for large s. So it definitely has different behavior, and it's definitely not as exponentially soft as string theory. So let me just quickly tell you about the machine learning implementation. So as I said that we could do it using SDPB, but there is a way of doing this using machine learning. So we have a 2-layer neural network. So we are putting L and N as the input values, and the machine learning tries to impose these constraints. So you have these kind of constraints, and you also have the CNLs to be bigger than 0 because of unitarity. So the last layer actually imposes the fact that the CNL have to be bigger than 0, and then out comes the function. And one thing that you can ask is from the reconstructed function of L and N, can you see the reggae pole? And the reggae pole is supposed to be a straight line. And indeed, at least for the superstring case, it seems to be promising. So again, we don't have complete accuracy. You don't see exactly what you expect from analytical stuff, but machine learning seems to be learning the reggae pole quite nicely. So the second game that you can play, and this is, I said that I had fixed the spectrum to be integer values, integer space, mimicking string theory. Now you can actually make it random. So you say that I don't know what the spectrum is. I'll just select a bunch of random numbers on the real axis. I've not given any imaginary values yet because we are doing tree-level bootstrap. And you can again play the same game. So you want to minimize entangling power. This is the scatter plot. And the scatter plot is on the y-axis, you see the entangling power. The red line is the string value. And we have done the simulation around 250 times for 250 different kinds of spectrum. And all of them, again, repeating the same exercise, give you an entangling power that is above the string value. Okay, so somehow string theory seems to be minimizing this amount of entanglement that is generated. And this, I think, is an ideal thing to be, so this plot was generated using SDPB. And this, I think, is an ideal test bed for the applicability of machine learning. Because with this random spectrum, we won't be able to do things using SDPB. I mean, because the parameters of the spectrum sit in the denominator, so you cannot convert it into an SDPB problem. So this, I think, is something that would be very interesting to sort out, and this is something that we are actively pursuing, except that we have not figured out what is the best neural network to use. The convergence that we have found so far is quite slow. Okay, so are there any questions? Okay, so this was the kind of numerical games that you can play. These are very easy games to play. It doesn't take too much time. Also doesn't take too much resources. You can literally do it on a workstation, and if you're willing to wait long enough, you have a laptop lying around, you can do it on a laptop as well. Although I wouldn't advise it. I would suggest you have at least a 40-core workstation. Yeah. So that brings me to the second half of the lecture, and after showing you this plot, I will go to the blackboard, which is the Frossa bound. And it's also called the Frossa-Martin bound. So the Frossa bound is the upper bound for total scattering cross sections. And this is true for theories with a gap. So in particular, one should have in mind scattering of pions, or if you want something experimentally relevant, you want to extend this to proton-proton scattering or proton-antiproton scattering, and there are experimental results from accelerators. So this is the growth of the scattering cross-section measured in millibarns, plotted against log of the center of mass energy. And there are a couple of interesting features to note, that the PP bar cross-section actually differs for low energies, but both of them actually first decay and then start rising. These green plots, the green points here are from cosmic ray data, and the error bars are huge, so we don't really know where to place the points as of now. The error bars, hopefully over the next several years, is going to come down, and this plot is kind of outdated. The other thing to note is that there are places where the green and the red points are almost on top of each other. So the scattering cross-section for PP bar and PP, they actually become the same as you approach high energies. This is a famous theorem. It goes by the name of the Pomeranchuk theorem, and it's a consequence of unitarity. The other important point that I want to say is that bound this outside factor is pi over 4 m pion square. If you naively try to match it or do some fitting with the existing proton-proton data, that outside factor is off by a, it's actually too large by a factor of 100. And so there are two questions here. So is there a stronger Froissart bound possible, or maybe we have not approached the asymptotic region as yet? So there are two distinct possibilities so far as real data is concerned. But ultimately, I think this is a good challenge, because this bound, which I'm going to show right now, or derive right now for you, is using analytical results by assuming that you've gone to high energies. But Bootstrap, you don't have to do that. Bootstrap, you should be able to do that for any energies, and you can search for models, search for things which actually saturate or have this kind of a behavior at moderate energies as well. So that is one of the motivations why examining high energy bounds is interesting. And in fact, in the conference, there is going to be a talk by Andrea Guerrieri on this Froissart bound Bootstrap. Are there any questions? So then I'll just switch the screen off and go to the board. Oh. Yeah.
Chiral perturbation theory calculations or any lattice?
Matching up the Bootstrap. Yeah. So in fact, there have been attempts where you try to match up the chiral perturbation theory results and get a non-perturbative S matrix. So this is work by Yaffe Hay and Martin Kruczynski. And from there, you have some prediction and also by Andrea and company. And they have some prediction that there is going to be some new tetraquark resonance at 2 GeV or something along those lines.
So this is specifically for the pi-pi?
Yeah, that's specifically for the pi-pi, yes. So this is the second half of the final lecture. This is the Froissart-Martin bound. This is French, so this is Martin, not Martin. This was first found by Froissart in 1961. So he used, he leveraged something called Mandelstam's double dispersion relations. And Martha was able to fix the coefficient, but without actually using this double dispersion relation. He was using fixed T, and he had some amazing results for pi-pi scattering, which I'll mention. My derivation that I'm going to talk about, so the Froissart-Martin bound, let me just note it down here, is that the total scattering cross section. So this is the total scattering cross section. It's not just pi-pi going to pi-pi. It's the total scattering cross section. So this actually leverages the imaginary part of the amplitude and the optical theorem. So in the high energy limit is less than. Conservatively, they also put an equal to m pi squared. There's a factor of 4 here, and log square s by s naught. So S is the center of mass energy. S naught is some scale that makes this dimensionally correct, but this is like a fit parameter. So there is no first principles derivation of this S naught. although in the derivation that I'm going to present, you can fix this a bit more. The derivation that I'm going to present is due to Indurain, and this is from a 1970 paper. So he was talking precisely keeping in mind the pi0 scattering. So the first thing that you do is, so instead of thinking about this as a scattering cross section, which is a function of S, so you can you can start to nitpick and say that these amplitudes are supposed to be distributions. So you should really talk about averaged values of these quantities. Is you define some average sigma bar. You can think of this an average scattering cross section. It does not have the dimensions of scattering cross section, as you can verify, but then it's you will see what is going on. So one thing is that in this pi0, we actually have in the complex S plane the cut that starts from 4m square goes out all the way to infinity, and then there is also the corresponding U channel cut on the left hand side. So this is the analytic structure. So the first thing is that we don't really know what is happening at infinity. So we are going to justify whatever we are doing as it goes along. So you first define a quantity which is made up out of the scattering cross section. So you're just going to average from 4m square to some value S. So S is going to be large but not infinite. And we're going to take the total scattering cross section. And for reasons that will become clear in a bit, we will also multiply it by S prime minus 4m square. And as you can see, this does not really have the dimensions of a cross section because, sorry? Okay. So because this is the scattering cross section, there is something that has dimensions of m square here. There's something that has got dimensions of m square here. And there's only 1 over m square there. So strictly speaking, you should have squared it. But I will stick to Indurain's definitions. And
저 어플을 이용하시는 거죠?
oh, I see. The video is going off. Oh, see. Very good. Yeah, so we have defined some kind of an averaged sigma bar S, and we're going to try to bound this. So what I need are these two definitions, and I need to make this a little bit more precise. So in this particular case, because there is a theory with a mass, there is going to be this normalization factor outside. And L runs from 0 to infinity and only over evens because this is identical scalar scattering. And the final change is this is going to be S minus 4m square. So the absorptive part will also have the same normalization factors outside. This is minus 4m square. And the final ingredient that you need is the optical theorem. Optical theorem tells you that the total scattering cross section is related to the absorptive part in the forward limit. So the formula is simply in the forward limit, you will just set t equal to 0. So the total scattering cross section works out to be 16 pi over, so these are some normalization, S minus 4m square, summation over L. So here also there is a summation over L, 2L plus 1 eta ls. So in these normalizations, not only is eta L bigger than 0, but it is also less than 1. So eta L's lie between 0 and 1. So we are going to take this, plug it in here. So you're going to get you're going to get 16 pi over S prime minus 4m square, summation over L, eta L and 2L plus 1. Let's try it this way. So now you see the importance of introducing this factor. So this factor and this factor cancels out. And this average sigma bar is simply related to some averaging that you're doing of these eta L's. So this I can now split into two pieces. So first I'm going to split the sum. So I'm going to split the sum into two pieces. So I'll write it out here. So integral 4m square to S ds prime summation, and now there is a sum from L equal to 0 to capital L. And then from L plus 2, remember the L is even, that's why it's L plus 2, not L plus 1, to infinity to L plus 1 to L S prime. And the whole game is to basically put a bound on this object here. So the target is to put a bound this. So the first piece, what you do is you say that eta L has to be less than 1 for any S. So everything here is positive. So this whole thing is basically 16. So the first term here, so let's write it here. This thing is just going to be summation over L equal to 0 to L, capital L, 2L plus 1. And this has to be less than equal to, because eta of L is less than equal to 1. So I'm setting, in this sum, I'm setting eta L to be equal to 1. So this 2L plus 1, I can just pull it out. And then this integration simply gives me a factor of S minus 4m square. So this average cross section is less than equal to this quantity plus something that is positive. So plus this important quantity, let's call this star. So now doing this sum is straightforward. So for a while, I'll be careful with factors, but ultimately, I won't be that careful with factors. So for now, I'll be careful with factors. So this actually gives me, so what we have overall is sigma bar s is less than equal to 16 pi over s minus 4m square. And now I'm opening the brackets, that's a factor outside. So now let's do this sum. This sum is L plus 1 into L plus 2 by 2. And plus this quantity that we have to bound. So the logic is, and this is important to remember, is that if there has to be a bound, we have to show that there is an effective truncation in spin. Because if this L was allowed to go all the way to infinity, then there wouldn't be any bound. So somehow we have to show that beyond a certain capital L, this term exponentially dies out or it goes to 0. So that's the logic behind trying to derive the Froissart bound. Is that clear? Is the target clear? Yes. This is L plus 2. Yeah, so you are only summing over even spins because this is identical scalar scattering. So if you are scattering identical scalars, then you don't have the odd spins. I'm sorry?
What was happened in the result of the polynomial at the average?
Oh, so the optical theorem was a statement in the forward limit. So t was equal to 0. So PL of n is PL of 1 is 1. Okay, so in this particular case, there is no Legendre polynomial. It is going to appear in a bit through another condition. Okay, so right now at the level of sigma bar, there is no Legendre polynomials. Okay. So target now is to bound this. So this is where a new notion comes in, which goes by the name of polynomial boundedness. And what this is telling us is that the amplitude is bounded for any t in the following way that enables us to consider this integral. Let's call it S prime. So this is a large circle at infinity. So this is in the complex plane in the S prime variable. So the polynomial boundedness is a criteria that enables us to consider this integral on the large circle at infinity and say that this is equal to 0. Okay. A game that you can, and I encourage you to play, is that you start off by modifying this condition. And there are lots of very easy games to play. One game that you can play is that I've been talking about this W00 in the previous slides. So you can say that, okay, let's assume that W00 is bounded. Then how does the following analysis change? Okay, so that's an interesting game to play. And the conclusion is, if you do things correctly, is that if you try to just impose the boundedness of W00, you get no constraint for this capital L. So in the original derivation, this 3 was replaced by n plus 1. N plus 1 was, n was kept arbitrary. And later on, the bound was in terms of n. And then there was some more sophisticated theorems by the name of the Fragman-Lindelof theorem in complex analysis that was invoked to fix n equal to 2. So, but we are going to assume that n is equal to 2 from the very beginning. Okay, so this is the polynomial boundedness condition. And then what you can do is, you can now Taylor expand this, because obviously there is going to be some pole contribution that comes from S prime square term in the Taylor expansion. And so this gives rise to, so let's write m of S prime at t equal to 4m square to be equal to a0 plus a1 S prime plus a2 S prime square plus so on. And we know that this amplitude has a cut from S prime equal to 4m square to infinity. So there'll be a contribution that comes because you're going to pick out this A2, and there is going to be a contribution that comes because you're going to pick up the contribution from the cut. So this is the same thing, same game that we played in deriving the dispersion relation. The condition that you're going to get is A2 is equal to 1 over 4 pi 4m square to infinity, the absorptive part of the amplitude S prime 4m square divided by S prime cubed. Okay, and the statement is that by construction this object is finite because this exists, so it has to be finite. And we are going to now massage this quantity here to extract a bound for this sum here in terms of A2. That is the next step. Yes, yes.
Usually we assume, Taylor expansion is usually assume the smaller s, but we are taking the integration at the very large x.
Yeah, so the idea is that you are going to get some large arc where this is equal to 0, and then there is going to be a pole that comes because of the A2 term, and then there is a contribution here. So you're shrinking the contour and picking up the relevant contributions. Yeah. Okay, so now with this A2, again you play the same game. So A2 you expand in terms of, so we know the formula for the absorptive part. So here we are going to use this formula that I've written here. So instead of actually writing out big expressions, let me just indicate what is going to happen. So you're going to put in the partial wave expansion. And then again, you're going to split the partial wave expansion into two pieces. So one of them is from L equal to 0 to capital L. And then the other one is from L equal to L plus 2 to infinity. The other fact that you need to know is that when t is equal to 4m square, inside the integral, s is bigger than 4m square. And when t is equal to 4m square, this quantity becomes 8m square divided by s minus 4m square. And so that quantity is bigger than 1. So this argument of the Legendre polynomial is bigger than 1. And one thing that we know about Legendre polynomials is if the argument is bigger than 1, then the Legendre polynomials are positive. So typically when you plot, it oscillates, but then if the argument is bigger than 1, it's positive and it is monotonically increasing. So basically the Legendre polynomials can do something like this, and then it becomes, after 1, it starts monotonically increasing. So that's one thing that we know about Legendre polynomials. So basically you have the first piece. This one is bigger than 0. This one is positive. So the first piece, all the quantities are positive. So this is again bigger than or equal to 1 over pi integral 4m square to, now we can again split this integral from 4m square to s and from s to infinity. So let's do that split first. So 4m square to s. So this is, I'm going to put a wiggle so that I don't keep writing, and then there is going to be an integral from s to infinity. Whatever is entering here is again positive. So we can write this is bigger than or equal to the integral from 4m squared to s. And then finally, whatever is sitting inside this integral where the sum is from 0 to L, that is also positive. So this is still bigger than or equal to ds prime over s prime cubed summation L equals to L plus 2 to infinity. And now we have to copy those factors there. Square root of s prime or s prime minus 4m square and then 12 plus 1 eta L s prime. And this is where the Legendre polynomial enters. 1 plus 8m square over s prime minus 4m square. Are the manipulation steps clear? Okay. There's another property of Legendre polynomials that you need to know. If x is bigger than 1, then the Legendre polynomials are also monotonic in the L. So PL plus 1x is actually bigger than PL of x. So inside here, the smallest value that we can have for the Legendre polynomial is when L is the smallest value. So L can be replaced by L plus 2. And you can pull that guy outside the sum. And the other property that you need to know is that once x is bigger than 1, the Legendre polynomials are monotonically increasing. So this property monotonicity enables us to replace this little l by capital L plus 2, that is the lower limit of the sum. And the smallest value of this is going to be when this guy is smallest, and this guy is smallest when the argument is from the upper limit. So what you get is this is bigger than or equal to integral 4m squared. So we can just pull that factor out. So this is going to be PL plus 2, 1 plus 8m squared over s minus 4m squared. And then you are left with an integral 4m squared to s ds prime over s prime cubed. And then there is s prime over s prime minus 4m squared. Summation 12 plus 1. And the limits of the summation are L plus 2 to infinity, eta L s prime. Okay? Again, we want to replace this whole object, this guy here, by the smallest value that you can take inside the integration domain. So we can pull that factor out as well and replace s prime by the upper limit. And since s is large, so s is much, much bigger than 4m squared, this quantity here we can approximate to 1. And we will have 1 over s cubed, PL plus 2, 1 plus 8m squared. And now we are putting in this condition that s is much, much bigger than 4m squared. So we are going to approximate this to be just s. And now you have this integral 4 to infinity, 4m squared to infinity, ds prime summation 12 plus 1 eta L s prime. And this is exactly the thing that we wanted to bound. So this is this thing from this inequality here. We can see that that sum there is, oh, I forgot to give the integration sign. So there's some integration sign that I forgot here. So that object here is bounded. It is less than or equal to A2 times S cubed divided by this Legendre polynomial. So that's almost, we are almost there in deriving the bound. So this object here, so together with the first term can be written as, and now we're going to make the approximation that S is much bigger than 4m square. So we will drop the 4m square compared to S wherever possible. And also we are going to anticipate that capital L is big. So we're going to try begin approximating this. You can just, so L is much, much bigger than 1. So this is just L square by 2. You will see that L is bigger, much, much bigger than 1 from the solution. So we can just anticipate that. And this is A2 times S cubed divided by the polynomial. Almost there. And the final magic is to impose a further non-trivial property of the Legendre polynomials, which is this 1 over PL of x for x bigger than 1 is less than or equal to pi by some phi naught. Phi naught I'll specify in a bit. So phi naught is some angle that lies between 0 and pi. It's not important. It's a non-zero. It's something that makes this cos of phi naught non-zero. We won't require to optimize this. You can optimize this if you want, but it is not necessary. So we will just focus on this term, the correction term, because this actually tells you that A2S cubed divided by P of L. And now because L is much, much bigger than 1, we can forget about the 2 as well. So PL 1 plus 8m square by S is less than or equal to 16. 16 is not there, so it's A2. So we can pull this S inside here. So let me just put that inside. So 16 pi over S. So one of the S's cancels out. So let's call that star. And star is equal to this. So this is 16 pi A2 S square pi by phi naught 1 plus cos phi naught. And now this guy x is 1 plus 8m square by S. So x is 1 plus 8m square by S. So S is large, M is fixed. So this is like a small correction to x. So we can actually just Taylor expand this quantity. So 1 plus 8m square by S whole square, that 1 and that 1 cancel off. And you're just left with the cross term. And you're taking the square root of the cross term. So this is where this is important, because the square root of the cross term is going to give me 4m divided by square root of S. This square root of S is very important. This square root of S is very important. It plays a very crucial role. And raised to the power of minus L. So from this quantity here, we have to determine L. So the next step in the logic is determine L, or L equals to L star, such that for L bigger than L star, this quantity goes to 0. Yes. Oh, because we are anticipating, and this is going to be a posteriori justified, that L is much bigger than 1. Okay. So just to simplify and not keep writing L plus 2 and blah, 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 to simplify my life, I've just replaced this by L. Yeah. So here we have anticipated that L is going to be much, much bigger than 1. So to solve this, you take whatever is inside here, including the 16 pi if you want, but basically I'm going to just focus this and exponentiate it. So this object is exponential of 2 log s plus some constants, but the main thing is going to be this guy minus L log 1 plus cos phi naught 4m by square root of s plus dot dot, and these dot dots are going to be made up of 16 pi and a2. The 16 pi and a2 is going to make this quantity dimensionless. So right now I have not worried about these factors, but you can actually be careful and work only with dimensionless quantities. But this is basically what you want. So L star is going to be fixed by the solution that this guy here is equal to this guy. And we can do a further expansion because remember that S is big, cos phi naught is finite, m by square root of s is small. So we can actually further expand this. And this actually implies that L star times some number divided by square root of s. This some number is this combination of cos phi naught and 4m is equal to or is proportional to log of s. So the spin cutoff, the effective spin cutoff, L star, is going to be equal to square root of s times log s. So this implies the effective spin cutoff in the sum that follows from unitarity conditions is square root of L log s. So that is the main result, that beyond this L, everything is exponentially small, and as a result of which you can throw that guy away, and then you get less than or equal to, and I'm going to put a tilde here because I have not been careful about the outside factors. It is simply going to be L square, and then there is a factor of s downstairs, and so you're going to get s times log square s divided by s, so that factor is basically going to be log square s. Okay, so sigma bar is less than log square s, and that's basically what we were after. Okay, so this implies that sigma taught, and you have to do a little bit more work to show this because I worked with sigma bar, which is an integral, but this actually also translates into the condition that this is less than some number, which you can determine by being more careful, is less than log square s. So the key thing was to reach this step where you are able to determine where the spin sum gets cut off. And again, to reiterate, the spin sum gets cut off because of unitarity, and that is the reason why you get a bound. Okay? Yes? Yes? So if you did this calculation in higher dimensions, instead of Legendre polynomials, you'll get Gegenbauer polynomials. And you'll get a version of this Froissart bound in any dimensions. And basically the outside factor changes. But it is similar in spirit. And you'll always get some kind of a spin truncation that happens in the forward limit because of unitarity. Yeah. Yeah, so that's a great question. So this is again sort of motivated by these are kind of hand-wavy explanations, but this is actually motivated by locality that your amplitude for any SNT is supposed to be. So the thing is that you're making a statement about the boundedness of the amplitude in the largest limit for any t or some t. So here we put the biggest value of t that was allowed. So I did not actually tell you why we chose t equal to 4m squared. So this is actually something that that Martin discovered, that the biggest value that is allowed in these kind of calculations is 4m squared. So because if you had chosen t equal to 0, you would get no bound. The Legendre polynomials would get replaced by 1, and then there wouldn't be any bound. So the objective there were a couple of objectives. So one of them is to choose the biggest value of t that is possible. And the biggest value of t translates into via this kind of a calculation, because you see the biggest value of t is related to 4m. 4m is sitting here. And so that 4m becomes quantity that sits in the denominator here. So the spin truncation, the sharpest bound that you're going to get is when you have the biggest value of t that is allowed in these calculations. Okay, so that is one thing. So that is one extra input that I did not tell you where it came from, and that is that was discovered by Martin, by the so-called Lyman-Martin ellipse that enabled you to actually put t equal to 4m squared. And the second assumption is this polynomial boundedness criteria. So this is somehow tied in with locality, the fact that your amplitude for this particular choice of t still remains bounded at large S. Okay, so this is an extra input, yeah.
Why specifically is that? Why particularly about power of S on the denominator? Why not say S squared or S to the 4?
Which power of S?
It was the 1 over S cubed.
Okay, yes. So as I said, the derivation can be carried out without actually specifying what power of n there is. So you see, where did that power come? So this 2 came because we assumed that it was s cubed. If you were to assume that it was s to the power n plus 1, then you'll see an n here. So that would actually mean that there is an n sitting here. So the power of log does not change, the coefficient will change, and the sharpest thing is going to appear when you actually have the smallest value of n allowed. And so this, there is some logic here that after this, if you leave n arbitrary, you can, using some sophisticated complex analysis techniques by the name of Fragment-Lindelof principle, you can actually show that that n is 2. Correct. And so as I said that this log S basically came because of the polynomial boundedness. So imagine that you did not have any polynomial boundedness, you wouldn't see any power of S here. Okay, so it is vital that you have this log S, and that is a statement about polynomial boundedness. The square root of S is just a property of the Legendre polynomials, but crucially, I needed to have the biggest value of t possible here, because imagine that you weren't allowed to go bigger than t equal to 0, then again there wouldn't be any bound. So this was also important to see this spin truncation.
A little conceptual question. Yeah. So Froster bound really applies to gapped theories.
Yes.
And you were mentioning PP and PP bar cross sections, and we know that in real life, it's not gapped.
Yeah. So I think that is the statement that these kind of things where massive particles dominate the exchanges is a property of